Right now we need to solve problem number 1. In that problem we need to implement some state equation in continuous time, and using that state equation we are in condition to implement some discrete time version of the state equation. We will use for that the Euler approach. It's an approximation. In particular, it's very useful for us for dealing with nonlinear system for which we don't have a closed form this time version. So the first step that we are going to implement here is going to create a file. I will call this my function main, and here I'm going to do certain things. One of the other functions that we need to implement will be the state equation. So this is my state equation. Yeah, and that state equation should return certain variable and should have certain argument here. If we are following the convention or the concept that we saw during the lecture about state space representation, you remember the case of the pendulum, which is the one that the system which we want to apply here. So this should have two arguments. Who are those? Well, this is the state of the system. When I call this function at this time, this is the state of the system, and this is the value of the input at the same time. And this function should be in condition to return the derivative of the state of the system at that time. So I will call this function dx dt. And this function will implement that thing here. So for the state of the system, let's remember that this state vector, just to remember what is the state vector, this state vector has two components. For this case, it's a two-dimensional vector, x1, and we have, using the MATLAB convention, will be a 2x1 vector. It will have these two components. So we want to create two variables with those names. We want here to explicitly show this so it's easy to understand. So this should be number 1. Yes. And this should be number 2. We don't have the obligation to do things in this way. You could use the vector here, extracting component or subvector, or directly the full vector in certain expression, and that would be okay. I'm trying to create copies in these extra variables, so for us it's easy to visualize this when we compare with the equation that we have. Alright, so we should be in condition to provide also certain output of our implementation here, returning that variable, and that one should be composed in this case as well by two components, which are each of them the derivative of the corresponding component in the state vector. See, we should be in condition to implement this thing. Alright, so who are those? Well, we need to calculate these things. We need to implement certain equation here. And according to the model, the derivative of x1 respect to the time should be x2 for the state space representation, for the state equation which we are talking about. That is what we saw in that example in the lecture. And this one should be something similar to this. Put that thing. This is what I want to do. Okay, this is my state equation. Everyone is happy with that. Okay. I should put equal here. Okay, everything is in place. I'm returning this vector, which contains the derivative of the state vector with respect to the time, according to our model. Everything seems to be correct here. Okay. That is clear for us. Now, oh no, I don't want to do that. I want to separate this piece of code so we realize what is each part of this code. Now I want to run a simulation using this state equation in a discrete fashion so that I will have certain steps, small ones, to do our Euler approximation. Suppose I'm using 1 millisecond for, and suppose I want to run a simulation from 0 to TF, which is 10 seconds. Suppose that. How many iterations should we have? Well, I will put here, well, it should be, in this case, TF minus the initial time, which is 0. Whoop. So I will put here dt. In this case, it's going to be exactly, this is one part in 1000, dividing this, it will going to be 10,000, but in general, maybe give you a fractional number. So I will put this thing, which is going to give me the lowest integer, close enough to that number. But in this case, the number was already an integer, so it's going to be the same number. So that means that if we implement some loop here, that will be composed by this number of iterations, which is going to be 10,000. Okay. Good. What should we do here? Well, I will have a state vector, which I should initialize here. Initially, I put this value. And what I'm going to do is to obtain this thing by calling my state equation. Yes. And it should produce that thing. I'm going to provide this value always, and I need to specify also very soon. We have to do this soon. So that if we know the derivative, we could apply the Euler approximation. I think that the x is going to be modified. It's going to be equal to the original value plus certain displacement, certain change, which I'm going to specify that is delta time, in our case 1 millisecond, multiplying the derivative of the state of the system respect to the time, which we got from here. That will do what we want to do. So everything is in place here. We specify the initial condition, we run the loop, we apply this number of iterations. I always get the derivative of the state vector respect to the time using the state equation, and I exploit that for implementing here the Euler approximation, and that will be producing the different value of x. And the value will be different in respect to others they had before each time. Then we run an iteration and we get the derivative and particular input is affecting that derivative. So what input should we use here? Well, I create an array here to put some 10,000 or n values, each of them corresponding to each of the indexes here, each of the discrete time. So I would say that I could modify this. Initially it's plenty of zeros when I create this thing here, but I say that from 500 to 2000, so which is from 0.5 seconds to 2 seconds. I want to force that sequence to be equal to 1. I could add other variation, 3000 from 3 seconds to 4 seconds equal to 2. So we are creating that vector, that array, which we will use to specify the input u at each of the times, discrete times. Yeah, that's okay. This value which we apply here, okay, it will be, maybe it will be different at different discrete times. This seems to be doing the job. Everything that we need is here. All right. Now we're implementing this program because we want to try some short-term simulation or prediction. and we want to plot whatever happened to the value of the state vectors during that horizon of discrete time, from 1 to n, or from 0 time to 10 seconds. For that, what should we do? What is possible to be done? This is a possible thing to do, implement in MATLAB, in this case to keep this program small, a sort of buffer. So I have this rectangular metric here, which is 2 by 10,000. My intention is that at each iteration I will set one of the columns of this rectangular metric to take a copy of this value of the state of the system at this time. So I will be filling this buffer, and that's okay. That will be good for my experiment. After that, I don't want to do this now. After that, well, what should I do? I want to show this. I want to save this in a file. What should I do? Okay, let's plot this. I will create a figure. Yeah, and it will be a certain figure in MATLAB. I will clear that figure just in case. And I may plot some of the variables of interest for me. Everything is in this buffer. I will plot the first row and all the columns that correspond to the recording that we have about the state x1 and the different discrete times. I will plot this in blue with dots. Okay. Now why it's not pressing the proper key? Good. And I also may plot the other variables. Should I put in different figures, or should I put all together in the same figure? What would happen to be that each of these variables which are of interest for us, they are representing different physical variables. They are in different units. They are not scaling in a way that visually we could appreciate together, all of them. So for that, I'm going to better to create some subplots in this figure. I will create 3 vertical, just one column of subfigures, and this is what I have here. I will put some label. Is x1 initially certain units, which I'm not going to show now. And I will do the same for plotting the second component, which is going to be this, and that will correspond to the second one. And I also want to plot how was the input. So this will be the last plot. And here, array with the sequence of inputs. I will put this in black. I will put this other in red. And I call this U of the time. Yes. Okay, this seems to be what I wanted to do. Yeah, let me see. Okay, this is problem 01. Good. Right. Seem to be good. Everything. I should be able to run this program. Okay, I don't see the figure on MATLAB complaint. I think I'm missing something. Let's do some verification. And it's not in any. Oh, and oh, I should put this after I calculate n. That was the complaint. All right. Now here is the plot. Yes, this is the plot. This is the input. Okay, it was 0, jump to 1, jump to 0, jump to 2, jump to 0. That was the input u of time. And this was x1 and this was x2, how they were evolving through this experiment or this test. Okay, what should I improve this? Well, maybe because if you analyze this, they are in radian and this is in radian per second. But you may tell me, well, I don't like to see these angular variables, angular position and angular velocity in radian and radian per second. I want to see this in degrees. So I will create certain constant for proper scaling. Okay, so if I put this thing here, I'm going to convert what it was originally in radian or in radian per second, and then it's going to be in degrees. X1 in degrees. Okay, and also this one, X2 in degrees per second. Okay, and the last one was the input. No, this should be labeled, no label. Something label, label, and Control C. For this one, I will mention here that this is U of time. Specify the unit. I may also show the time in second in place of using okay, let's say 0 to and minus 1 multiply dt. It will give me the 10,000 or n times expressing them in seconds. So I could plot these things against the time. Please, let's see if I didn't introduce any error. No, that seemed to be okay. It was the input. Now the time scale is 0 to 10 seconds. Yes. If I want to complete this properly, I should have also certain, at least in the last figure, sub-figure here, I should have the horizontal axis, and this should be the time. In this case, time in seconds. Okay, I'm introducing a lot of mistakes in my keyboard. Everything now is correct. Here is, this is in degrees, this is in degrees. Sorry, this should be, I think I'm plotting wrong thing. This is wrong here. Okay, X2. This is very unusual because I would expect this not to be equal. So initialize, but in the example or in the problem, they are telling us that the initial condition for our case was that the angular position, the angular initial value was 90 degrees, and because my program expect to work in radian, so I will express this 90 degrees but in radian, and the angular velocity was 0 in any way that we express that. Now I did run this, and I could verify, yes, that my plot is starting at 90 degrees and it's oscillating here because it seems to be the torque we apply is not so aggressive. But still, there will be some effect with respect to a system not having any input. Okay, I think we cover everything here. We did cover everything. Stop the recording.